Hi everyone! Today we're doing something I'm really excited about, using our large format film camera for macrophotography. I had a great time making this video, and there's a really cool demo of optics in here that you should not miss. So stick around and enjoy. So what is macrophotography? Most people associate it with close-up photography, and that's not wrong. They're both closely related but not exactly the same. Macrophotography has a very specific technical definition that sets it apart. It's photography that achieves a reproduction ratio of 1:1 or greater. But what does that even mean? I could just explain it, but where's the fun in that? So why don't I show you instead? Here we have a setup that demonstrates the basic optical principles of a camera. It includes the three essential elements of taking a photo. The first element is the subject. This is what you're trying to take an image of. I'm using this battery, which I've mounted on this special stand to keep it in place. Next is the lens. This is the part of the camera that sees the subject and projects an image of that subject to our last element here at the back, which is the medium. The medium is what captures the image. In analog photography, the medium is the film. In digital photography, it's the electronic sensor. For our demo, we are just using a white piece of paper inside a 4x5 film holder. All these parts are mounted on a yardstick, which you can see here, which acts as a rail, along which any of these elements can move freely. Now let's go ahead with the demo. For this part, we have to turn the lights down quite a bit. Note that right now, there's nothing on the medium. To start, I will turn on a flashlight right here that will illuminate the subject. I want you to keep an eye on the medium. Now, we see a spot of light appear on the medium. This spot is actually the unfocused image of our subject. We need to move the medium along the rail to make the image look sharp. So here we are, looking at the image up close. Let's move the medium until we get the image in focus. There we have it. You can see a sharp image of our battery on here. Let's take a quick note of how far the medium is from the lens, as we will need this info later. So right now, the lens is sitting at the 6-inch mark of the yardstick, while the medium is sitting at the 13.5-inch mark, which means they are 7.5 inches apart. The next thing I'm interested in is to see how big or small the image of the subject is compared to the real thing. Going back to the image of the battery on the medium, I'm just gonna place the real battery right next to it. Here. We can see that the image of the battery is much smaller than the real battery. The battery on the image seems to be half as tall as the real battery. The ratio of the size of the object's image versus that object's actual size is what we call the reproduction ratio. In this case, we saw that it was approximately 1:2. Remember that we defined macrophotography in terms of the reproduction ratio. That is, it is photography with reproduction ratio of 1:1 or greater. In other words, macrophotography is just photography where the size of the image projected on the medium is the same as or larger than the size of the actual object. With a ratio of 1:2, our setup is not quite macrophotography yet. The 1:2 is commonly considered to be the starting point for close-up photography. So how do we achieve macrophotography? An obvious first step is to just move the camera closer to the subject. As we move the camera elements forward, the image on the medium gets larger, but it also becomes quite blurred. We need to do the focus adjustment again by moving the medium. Now it's sharp again. Let's see one more time how the size of the image on the medium compares to the real-life size of the object. So it looks like we have achieved very close to the 1:1 reproduction ratio. Let's also measure the distance between the lens and the medium. I see here that the lens sits on the 0-inch mark, while the medium sits close to the 11-inch mark, which means that our image distance is close to 11 inches. This is longer than the 7.5-inch distance that we have previously noted. Changing the distance between the medium and the lens is actually how focusing works. The distance from the lens to the subject, which we'll call the object distance, and the distance from the lens to the medium, which we'll call the image distance, are inversely related. As you move a subject closer to the lens, the distance between the medium and the lens needs to be increased to maintain focus. Sounds simple enough, right? If we want to get even larger reproduction ratios, could we just keep moving the subject closer to the lens until they are right next to each other? Do we just need to push the medium as far back as it can go? The reality is, it's not quite so simple. The two distances, object distance and image distance, are related by what we call the thin lens formula, which you can see here on the screen. The thin lens formula just provides a relationship between three variables: the focal length of the lens, the image distance, and the object distance. We're not going to dwell on this form of the formula, but let's rearrange it so that only the image distance is on the left side. We are interested mainly in the relationship of the image distance and the object distance, so let's treat the lens focal length as a constant for now. With just a formula, it can be hard to grasp what it tells us exactly about how the two variables are related. What would give us a better sense of the relationship is this graph, which plots the object distances against the required image distances. In generating this graph, we have fixed the focal length to be 135 mm. The x-axis on this graph represents the object distance, while the y-axis represents the image distance. Each point on this graph represents a combination of object and image distances that will show a focused image, assuming that we are using a 135 mm lens. We can essentially separate this graph into two parts that each behave very differently from the other. Let's split the two parts at x is equal to 600 mm, or 0.6 m. We'll call the part to the left of this point the close-up region, and the part to the right as the normal region. The object distances in the normal region represent normal photography, where the subject can be as close as just a few feet away to as far as infinity. As you can see, the graph in this region looks quite flat, meaning that the image distance does not need to change by a lot to achieve any object distance within this huge range. If you focus at an object just 0.6 meters in front of the lens, you need an image distance of 175 mm. If you focus on an object at infinity, say a star in the night sky, the image distance approaches 135 mm, essentially the focal length of the lens. So we only need 40 mm of focus extension for such a large range of object distances from 2 feet to infinity. Most general-purpose cameras, like your phone camera, work at this region. This is the most common way cameras and lenses are built because they are the most commonly used and relatively easy to incorporate into a compact design. Now let's look at the other region here on the left. This is the region for close-up photography and macrophotography. Here, the behavior of the relationship is the complete opposite of that of the normal region. It looks much steeper, which means that a small change in the object distance require a large change in the image distance to maintain focus. As we mentioned previously, at 600 mm object distance, you need an image distance of 175 mm. But if we bring the object closer, to 300 mm for example, we need an image distance of 240 mm, which is an increase of 65 mm. That is already much bigger than the 40 mm we needed to change focus from 2 feet to infinity. If you move the object any closer than 1 foot, the image distance just skyrockets. In fact, as the object distance approaches the focal length of 135 mm, the image distance approaches infinity. This essentially means that it's impossible to focus on an object when that object is 1 focal length away in front of the lens. I have added an orange point to the graph to show where macrophotography actually begins. At this point, image distance and object distance are equal, and they happen to be 2 times the focal length, or 270 mm in this case. Interestingly, the reproduction ratio can also be computed as the ratio of image distance to object distance. To the left of this point, the image distance gets larger as the object distance gets smaller, so the reproduction ratio is increasing. We mentioned that it is easy enough to make cameras that work at the normal object distance range because they can be quite compact. It's still quite easy enough to create cameras and lenses with reproduction ratios of 1:1, and this is typically the maximum for most macro lenses. But it becomes quite challenging to go higher than this as image distance increases very rapidly. Surely, one can just build a longer and bigger lens to accommodate the longer image distance, but only up to a reasonable limit. Moreover, there are other problems with long image distances, like light fall-off, that we are not discussing here. As far as I know, the highest reproduction ratio achieved for a commercially produced DSLR macro lens seems to be at around 5:1. Now, let's put all that demonstration and discussion aside and actually try to take our macrophotography image. This is the large format camera that we will be using today for macrophotography. This camera is what is called a view camera, or alternatively, a monorail camera. This one is quite old, probably more than 50 years old at this point. It is a film camera that uses a 4" by 5" film negative, just like this one. The design of this camera is very similar to the demo setup we had earlier. The camera consists of 2 frames, one in front of the other. The front one holds the lens, as you can see here, while the rear one, as I'll show you, holds the viewing glass as well as a mount for the film holder. Both of these frames are attached to a single rod, also called a rail, that you can see here, and these frames can be repositioned anywhere along the rod. This camera also has collapsible bellows in between the frames to keep the space between the lens and the film light-proof. What makes macrophotography possible on this camera is the fact that it has a very long rail. This allows the film and the lens to be separated by up to 600 mm. 600 mm of image distance get us very generous reproduction ratios, especially working with lower local length lenses like the 135 mm that I have on here. So here's our camera, fully set up and ready to take a photo. The front stand and the rear stand are now as far away from each other as possible. The camera is already pointed and focused at our subject, which is a $1 coin. You can see here how the coin is mounted and positioned in front of the camera. Let's try to measure the reproduction ratio we are getting. We know that the diameter of the $1 coin is close to 1 inch. So let's take a ruler to the viewing glass and see the diameter of the image projected there. We see here that the diameter of the coin's image on the ground glass is around 3.5 inches. So our reproduction ratio should be close to 3.5:1. Now I'll go ahead and take the photo using color film, develop, and then print it. Then we can look at the photo together after it is done. So fast forwarding ahead, I've already done taking the photo. I've developed the film. I've made a paper print using the enlarger right here. Now let's take a closer look. So here's the results of our photography exercise. This here is our actual subject, the coin. Here we have our film negative. And then this is our final print that we made using a color enlarger on color paper. So to recap, from here to here, we had a reproduction ratio of around 3.5. So which means this one is the diameter of this coin in the film is 3.5, this one. And when we made the print, we made an additional enlargement of around 2 times. So this is probably maybe around 7 inches. So we start from 1 inch here, 3.5 inch here, and then finally 7 inch here. So you can just see how much detail we have here, right? Even from this viewpoint. But let's see what we can see if we bring it closer. So let's zoom in the camera. So you can see a lot of detail here. It's quite sharp. So you can even see these symbols in here, right? What's that like? I'm not sure what symbols those are, but yeah, I don't think I'll be able to see that on the actual coin. Maybe I could if I look very closely. But here you can see the lines on here on this feature of the image, and also here, right, on the torch. So there's some detail there. You can see also the dents, right, of the coin. So this one, right, it looks like a dent, and then this one, and this one also. So there's some scratches here, here, and here. So let's look around the edges, right? So what can we find here? So let's just go around quickly. This one's quite interesting. I'm not sure what it means. It must mean something. So the lettering is quite clear, right? So we can see also some scratches here and dents. So overall, it looks like a well-worn coin, right? And this one also, right? We can see some lines here. I'm not sure if this is intentional or not. But yeah, you can clearly see some lines here that's probably very small to see with a naked eye if you look at the coin. Let's see what else we can find. So and then it's good that we were able to kind of see a sharp image throughout, right? So I tried my best to have the whole surface of the coin as flat as possible to catch it in the focal plane. I think I did a pretty good job, and you can see also how shallow the what do you call this, the depth of field is, right? Because this coin is probably maybe less than 2 millimeters thick, but the feature on this background, so this is right, this is the a 3D printed surface. You can actually see that here. So there's some kind of, it's a bit rough, right? And you can see that here. So it's already kind of out of focus, right? So you can already see some diffusion or some blur there. So yeah. Let's see if we can zoom it in further and then just go around the image. All right. So there you have it. We've successfully taken a macro photography photo with a large format camera. If you have a large format camera, do consider doing this yourself, and I'd love to hear about it in the comments. If you have time, check out the other film photography related videos on this channel, like this one on the screen. Please don't forget to like and subscribe, and I'll see you on the next one. Bye!